Okay, so somebody asked me to teach functions, that is, yeah, I mean, like, go from top to bottom, teach it actually. So that's what I'm going to do. I'm going to do the in chapter exercises, and at the same time I'm actually going to teach the theory. So let's start. First, you got an ordered pair. An ordered pair can be given as a comma b. So these round brackets, those mean ordered pair. If you got something like this, a set, so a comma b, this is an unordered pair. That is, this thing is the same thing as the set b comma a, but then the ordered pair a comma b is not the same thing as b comma a if a and b are distinct, that is. Okay, so that's understandable. Then you got Cartesian product for sets a and b. It is the set containing all ordered pairs. Okay, so a cross b is given by a comma b, such that a belongs to a and b belongs to. Cool. So for example, if you got set A as 1, 2, 3 and set B as 1, 2, 3 as well. So the cross, that would be like, first you got 1 over here, you're going to pair up all of them, right, with 1. So it's going to be 1, comma 1, 1, comma 2, 1, comma 3. And then you're going to do the same thing for 2. So 2, comma 1, 2, comma 2. And then 2 comma 3, and then same thing for 3 as well. So 3 comma 1, 3 comma 2, and 3 comma 3, right? So once you got all these ordered pairs, just put them in a set, and there you go, you got a cross b. So this thing is going to be your a cross b, right? Yeah, that's what this definition means. So notice that over here, all of the a values, those belong from the set A, and all the B values belong from the set B, and you are having all such A and B such that this can happen, right? So what are these results? Two ordered pairs A, B and C, D are equal if and only if A equal to C and B equal to D. That makes sense. Okay. A cross B is equal to C cross D. If and only if A is equal to C and B is equal to D. Of course, because all of the things on the left part of the ordered pairs, so our a values, small a values, those have to be the same. So there's only one thing, a cross, yeah, okay, a must be equal to c. There must not be any extra element or any element that's less than what is contained in a, because yeah, if d is not a null set, okay, so either both b and d could be null sets. That would make sense. Yeah, okay, I don't think that's defined like that, because how can you do a cross on a null set? I don't know, okay. But yeah, that's all we need to know right now. Cool. Okay, a relation from A to B is a non-empty subset of A cross B. So how did we go to relations now? Oh, so it's sets and relations first of all, and then you will actually go to functions. Right. So yeah, till now there's talking about relations and sets and whatnot. So okay, a relation of, okay, fine, I know what that is. So a relation is kind of like a bunch of ordered pairs. So say I say 3 related to 2, then what I'm saying is that 3 comma 2 is an ordered pair in the set R, right? So R represents a relation. Yeah, so right, and this can also be written as 3R2, right? That's the way a relation is run. And there are a bunch of properties about relation, like it being reflexive, transitive, all that stuff. We're not going to do that yet. Okay, roster form by exhibiting a set of pairs. Okay, makes sense. Set builder form by standard description using a rule or formula. Right, just like we saw in here. So like this thing. Okay. All right. Yeah. By arrow diagrams. Yeah, I mean there's also another way. Okay, cool. As a Venn diagram. Okay, this is new. I have never seen that. Sometimes the relations are not between two different sets, but between the members of the same set. Oh, okay. So for example, let us consider the relation is a factor of on the set A, where A is given as 2, 3, 6, 8. As Venn diagram, the relation looks like the following. So 2, 3 are prime, and then 6, 8 are completely made of these primes. That's the important thing. So, right, 8 will be only connected to 2. Oh, you got 4 as well. Right, okay. So even though 4 is not here, yeah, fine, whatever. But there's no 4. There should have been a 4. And why is there no 3 over here? Okay, maybe this should have been 4. I don't know. Right, so 8 is related to 2 and 4 in that case. Or maybe 2 and, yeah, okay, is a factor. So the R thing, so R, basically this relation is a factor of, so when we say 2R8, that means 2 is a factor of 8. So that's representing this thing. So 2 going to 8, right? So you start from 2 and then you apply this relation, you go to 8. That makes sense? Cool. Right. And that's why 2 is related to 8 like that, 4 is related to 8 like that, because that's a factor of 8. 2 is also related to 6 like that, and 2 is also related to 4 like that, right? Cool. A lot more can be studied about relations, but our main focus is, yeah, of course. Then why did you even, explain all of this stuff, right? Word function is used in as casual conversation, right? Okay, so no casual conversation right now. First definition of function. Function is an association. If you want to be of these associated, then the association is called function A to B. The set A is called the domain of the function, right? We know that much. So here they just told you what domain is, what range is, what codomain is, right? So domain is the set on which the function is supposedly defined, right? Actually, no. On each element, you do have the function defined. So that's how the domain actually is. So the codomain is the set to which the function supposedly goes. So whenever they say so R to R a function f, right? So real to real. So all real numbers are the domain of this function f, right? But not all real numbers are the outputs of f. So f of x can be a right? The range of f of x can be a subset of R as well, and that subset is what we call as the range. Wait, didn't I just say range already? Okay, but yeah, I mean that's pretty intuitive. Range, right? How much can the function vary? What kind of so basically the set containing all the outputs of f of x. So for every input being in its domain, what output do you get, right? The set of all those outputs is the range, and then that range can be a subset of this codomain. So the codomain, I don't know why they do this, but well, whatever. Is there even a need for defining a codomain? Because why don't you just define the range? Okay, I mean, you already know the range. So why don't you just not define the codomain? Because who cares, right? And they said C of all elements of B. Okay, it's called a range. Said B is called the codomain. Right, but seriously, what exactly is, I mean, what's the function of that? I don't know. But yeah, that's the way they define the functions. But whatever. Second definition of a function is a rule. Yeah, I mean, you already know what a function actually is. I mean, you must have that much of knowledge, right? So function is just some kind of machine that takes in an input and gives out a certain output depending on what the input is. So if you got a machine like 2x, it will take x equal to 2 and give out x equal to 4, or okay, f of x is equal to 4, right? So that's what a function does. It's a rule, basically. A rule that can be applied on every element on the domain. Cool. Right, and then you got, what is this thing? Yeah, okay, the image of an element of A. So whenever you apply the function on some element, you will get some output. That output is what we call as the image, right? And the input that gives that output is called the pre-image. So if there's a single pre-image, that means the function, is like 1, 1, or well, whatever. We'll see that later on. Every x belonging to A is assigned some y belonging to B. So all the elements in the domain must be defined, right? I mean, the function must be defined on all the domain, all the elements of the domain, right? Okay, entirely used up. That makes sense. I said the codomain may or may not be entirely used up. Yeah. The function may assign the same y belonging to b to more than one x belonging to a. Makes sense. X squared, stuff like that, mod x. Okay. For no x in a, do there exist two choices of f of x, i.e., right? So a function is, yeah, it can be many one or one one. It cannot be one to many, right? That's the thing. So for example, the square root function is defined as the positive square root only because you don't want it to be a two-valued function. So you could have said that, you know, square root of 4 is equal to plus minus 2, but then when you try to graph out square root of x, so for only the positive values, because imaginary, okay, let's not go to that. So the square root of x, you know, the usual square root of x, it looks like this, right? Actually, it should be going to infinity, but whatever, you can see the thing. It's not that flat, something like that, right? Yeah, of course, a parabola, y squared equal to x or something like that, right? Yeah, that's how this looks. If you know, I use plus or minus square root of x. So if I, instead of, let's say, instead of defining square root of x as the positive number, when you solve the equation x square equal to, sorry, t square equal to x, right? The positive value of t. Instead of doing that, if we just say it can be a two-valued, you know, entity, that is, for some value of x, you will have two values of the function, right? Then it's not really a function because you don't know what value should be at, let's just say x equal to 1. X equal to 1, it will be plus 1 or minus 1. So what do you get out when you put 1 in there? And that's why a function can only be one value. So that's why we say square root of x is necessarily the positive value, right? Okay. Right. Note that the 1 and 4 are essential requirements for the definition of function, but whatever. The word rule covers different kinds of schemes from making assignments, where consequently, we have different methods of describing function. A function is expressed by means of an arrow diagram, as shown in the relation. Okay, a table. Okay, right. Isn't a function? A graph. Yeah, sure. A formula as an algebraic expression. Fine, fine, fine. Fourth definition is a special case of relations. We have described. Okay, yeah, we already know this. We don't need to do that. Okay, cool. Graphs of non-function relations, of course. So you got parabola, you got this circle. As you can see, you got two values over here. I just explained why this is not a function, and also why this is not a function. Right? Okay, that's x squared plus y squared. That squared thing, that means you will have two values. That is like the thing, right? Okay. And oh yeah, this thing. So this whole line, I mean, it has all of these points, right, on the same x value. That means this doesn't make any sense. Yeah, right. If this line was not there, it was just, you know, open or something, and you would close only one of these and leave other one as an open circle, then this would be a function, because then you only have one value for one value of x, right? Graphs of non-function relations. Oh, okay, these are what? Wait. This is a graph of, oh, okay, graph of function. Yeah, that's the thing. Right, this is a function relation, this is a function. You get the idea. Okay, cool. Codomain and range of the function. F A to B, then the set A is known as, hey, we already know that, right? You don't need to explain it multiple times. Just, you know, give us what one, many one, and all those kind of functions are. Okay, a one function or injective function, right? So a function f a to b is said to be one function or injective mapping if different elements of a have different f images in b, right? So that basically means that for no two elements of the domain should you have the same image, right? So for example, if we take the square function, then f of 1 is equal to 1, but f of negative 1 is also equal to 1, and that's why x square is not a one function. But if we take x cube, you will have f of 1 is equal to 1 and f of negative 1 equal to negative 1. If you actually look at the diagram, you will see it's just monotonically increasing, right? Yeah. Okay, this is supposed to be 0 slope because 3x squared. So like this, Yeah, and what does that mean? That means for some image, right? So some y value, you can only have one x value. So if you draw a line like this, so y equal to something, it will only cut this curve at a single point, so at a single x value, that is, right? So we already know that for a single x value, you can only have a single y value, but now you are also doing the other thing, that is, for a single y value, you can only have a single x value. That is, it's a one-to-one relation, right? So when I say 2x equal to 3, x can only be 3 upon 2. It cannot be anything else, right? So yeah, I mean, if you know the image, you can figure out the pre-image. If you know the pre-image, you can figure out the image, right? That's why it's one-to-one. Makes sense. And that's injective, right? Memorize this word injective because it's going to come out a lot of times. Okay, no diagrammatic need right now. Okay, cool. This function is always decreasing. Oh, whatever. I mean, I just showed one example, x cube is continuously increasing. We will figure those things out later on. First, just the definitions. Onto function, surjective mapping. So if a function is such that each element in B codomain is the F image of at least one element, basically what all of this really means is that the range is covering the codomain completely. That is, the range is equal to the codomain. Yeah, that makes sense. So for example, if you got a function like sine x, right? So you got a function like this. Right, it's going from, I don't know, if say negative pi to pi, I have no idea, and to yeah, okay, let's not include that because you just want one full circle, whatever. So negative pi to pi, and it goes till, what was I doing? Right, the range is just negative 1 to 1. Oh, you already got, yeah, okay, sure. So negative 1 to 1, it's inclusive of both of them, right? And I don't know, what should I choose for this? Sine x, okay, cool. So f is given by, f of x is just equal to sine x, right? This is the rule, this is the codomain, sorry, this is the domain, this is the codomain, right? Now you notice the thing that negative pi to pi is like this. So you have negative 1 and positive 1 and all the stuff in between. That's why the range of this function, and of course then you go down, so you don't have that anymore, right? You start decreasing. So the range of sine x is really just this set. What does that mean? That the codomain and the range are the same. Now, instead of that, if I had given the codomain being like negative 1 to 2, right, then it would not be the same. So yeah, the codomain is not the same as the range, and that's why it wouldn't be an onto function or surjective function, right? That makes sense. Okay, cool. All right, then that's done. Next, then then there's a bijective function, which is both injective as well as surjective. That is, for every image you can find out a pre-image, and for every element in the codomain, yeah, you actually have the image. That is basically, you know, the codomain is the domain of the inverse function, right? Yeah, I mean, basically if the function is bijective, you got an inverse. Yeah, okay. If function is onto, it cannot be into and what, right? So into and many one, these are the complete opposites of, I mean, everything that's not one, right? That kind of function is going to be many one, and everything that's not onto, that's into. Yeah, so the range is only a part of the codomain. That's an into function. That makes sense, right? So you're spreading the range, and then for some time it's just in the um, codomain, and then after some time it actually goes on the full codomain. So that's why into and then onto, right? Okay, well, whatever. Identity constant function. Identity function is just, you know, x, basically f of x equal to x, no big deal. Constant function is just some kind of constant, doesn't really matter. Basic elementary functions. The power function, we know that for even powers, you know, it's not 1 1, and it's like bounded and whatnot, right? And so odd powers, I mean, I'll already showed you an example. Yeah, exactly, y equal to x cube, that's the most obvious example. And then asymptotes. Okay, so this is 1 upon x square. Okay, this is 1 upon x. Yeah, okay, it's 1 upon x, right? Nature 1 1 into, so y into exactly, the range is all real numbers except 0. I mean, yeah, it doesn't actually have 0 in the, wait, what's the codomain? I mean, okay, you didn't actually give us the codomain now. N is rational or whatever. I mean, it depends on what the codomain is. If I just make the codomain to be the real numbers except 0, then yeah, you're done. It's an onto function, right? It really depends on what the codomain is. Okay, exponential functions. Y equal to a power x. Okay, I don't have to explain all this stuff. I'll do that while solving problems. Logarithmic functions, trigonometric functions. Okay, yeah, no need. Oh, and by the way, like tan x is actually an important graph that you have to remember, because sometimes, I mean, in physics, that is, you will have to use this, right? So in one of my videos, actually use this to approximate solutions for x is equal to tan x, basically. So maybe it's good to remember this graph. And then you got cot x, which we don't have to remember. It's just pi upon 2 minus tan x. You can figure it out on the spot. No big deal, right? Sorry, it's not tan inverse. Yeah, it's tan of pi upon 2 minus x, which you can say is like negative tan of x minus pi upon 2. So x minus pi upon 2, what does that mean? That is shifting the whole graph by pi upon 2 forward, right? Or backward. Wait a second. Yeah, well, x minus pi upon 2, what does that mean? That what, so if you got some kind of point x naught, y naught, right? Now this point, so for the same y naught value, you actually have to shift this to x naught plus pi upon 2 to y naught and y naught, right? Which means you're shifting the whole graph by pi upon 2 towards right. So, and then you are also inverting it because negative. So this graph just shifted would be like, like this. And then this is like pi or something, I don't know. And then negative of this graph, and this is the 0 mark, of course, would be like this. And does that match? Of course, that does match. Okay, next. What is this? Oh, secant x. We don't have to do this. I mean, yeah, we just don't have to do this. Most of the time, I don't think we'll be actually using this graph. Right, inverse circular functions. Okay, fine. Ooh, trig functions. It's like, just rotating by pi upon 2, because it's like sine y equal to x, isn't it? For some certain x values, that is. Yeah. So only for negative 1 to 1. And yeah. And also y is in some certain range. So this is actually important to remember, that the codomain of sine inverse, it's negative pi upon 2 to pi upon 2. Of tan inverse also, it's negative pi upon 2 to pi upon 2. Cosine inverse is actually 0 to pi, right? So you can see that over here. Okay, and then both inclusive, right? So 0 inclusive, pi inclusive, whatever. So cosine inverse is 0 to pi, then cot inverse as well, it's 0 to pi, and secant inverse, because it's just cosine of cosine inverse of 1 upon x, it's also 0 to pi, and then this thing similarly, it's just 0, it's negative pi upon 2 to pi upon 2. That makes sense? Okay. You don't have to worry about these graphs. You will never be using this most likely, right? This is something you have to worry about. And of course, you got minus some stuff. Well, okay, whatever. We don't care about that. We'll do that on the spot. Some special functions and their graphs. Linear graph. Okay, whatever. Modulus function. Right. I mean, this is something you will be using a lot. The graph of modulus function. Those other graphs, not so much. But this, yes, you will be using. Along with the step function as well. Signal function, okay. Just look at the graph, it explains itself pretty clearly. So for x equal to 0, and this is a piecewise definition, you will be seeing this a lot. Just get familiar with it. So it's mod x upon x whenever x is not equal to 0, and whenever it is 0, it's defined as 0. That makes sense? Okay. Basically for the right side, so the positive x values, it's 1, and for the negative x values, it is -1, and for 0, it's 0. Makes sense? Greatest integer function. A function is said to be a greatest integer function if it is defined as f of x is equal to, what is this? Okay. Yeah, I mean, come on, seriously. I mean, just wrote out this. Why did you write that out? This thing is the greatest function, right? Okay. Less or equal to x. Yeah, whatever. So the graph actually represents what this function does. Sometimes it's also called the floor function, and the integer part function don't get received by the integer part thing, because sometimes you might, okay, you got -2.1. What's the integer part of this? You would say it's going to be -2, right? But no, it's actually the greatest integer function less than or equal to this value. That's actually supposed to be -3. So remember, the integer part, that's just for casual speaking. It's not actually what it does, right? Okay. Right. Important identities. Yeah, we don't need that. We'll do that on the spot. Fractional part of x. So curly bracket x, right? It's x minus integer part of x. So it goes like this. So whenever, okay, just actually tell you what's going on. So for I'm just gonna do this thing for positive values. So you got the fractional part of 2. It's going to be 0 because it's actually 2.0 or something. Yeah. So there is no fraction. It's only integers. So x is just 2 minus integer part of x. Yeah. Okay. It is integer function of x. That's going to be equal to 2. That's going to be 0, right? Does that make sense? Okay, cool. And then you got 2.1. The fractional part is going to be equal to 0.1. Then you got 2.2. The fractional part is going to be equal to 0.2. And that's what's happening over here. You can see at 2, it is 0, and then it goes up. And then what will happen at 3 exactly? So 3 has its fractional part equal to 0. But what happens for 2.99999? What about that guy? That's going to be equal to 0.999. So as you can see, there's a skip down for this thing, right? So for 2, I mean, it's going up, up, up. So 2 to 3, 2 inclusive, 3 not inclusive. It's just going up, up, up. And then over here, it's approaching 1, but it never actually gets to 1 because it just goes down like that. So to 3. So the range of this function is just -1 to 0, 0 to 1. What am I doing? Okay, 0 to 1, 0 inclusive, 1 not inclusive. Oh yeah. Oh, so these people also gave us the range here, right? Nature many 1 into, so that's many 1, of course, because you draw a y equal to something kind of line, and then it cuts it at multiple, actually infinite number of values, right? So it's many 1, of course, and it is into yeah, well, what's the codomain, right? It depends on that. Yeah, you can't just say it's into without understanding the codomain. That's not correct. Discontinuous at every integer. I mean, of course it is. Wait, what? Yeah, right. I mean, you can see the jump down, right? So when you approach it from the left hand side, it's 1, but from the right hand it's 0, and then actually f of x value is 0 at that point, which means it's discontinuous because the left hand limit doesn't become equal to the function value. Okay, then you got rectangular hyperbola. Why are you doing this? It's okay. F of x is equal to 1 upon x, right? So the 1 upon x function, what about that? It's a discontinuous and 1 into function. Once again, you have to define a codomain for okay, whatever. If it is going from real to real, then yes, it's an into function. But what if it's just going from real to real minus 0? Then it's a non-2 function, isn't it? So domain is all the real numbers except 0. Makes sense, because at 0 it's not defined. Yeah, I mean, you can see why it's not defined. It's going negative infinity and positive. Left hand limit and right hand limit don't match. Right. Transformation. If graph of y equal to fx can be known, okay, then to find graph of, yeah, okay, I just showed you that x minus h is shift to the right hand side by a, and this will do the opposite because it's like f of x minus of minus a, right? Of course. Okay. And yeah, this just, I mean, this is the easier one. So x plus h just shifts upward. This shifts downward. Cool. X upon a. So you know you had a point x naught, y naught. Now, so for x upon a, right? So for the same y naught, you should actually have ax naught as the point. So it actually stretches out the function by a, right? And then f of ax compresses the function by a. Makes sense, right? So this is y of f of 2x, right? This stretches the function 2 times horizontally. Wait, which one? Oh yes, x upon a, right? That's the one that stretches out horizontally. And then this compresses the graph. Okay, cool. See more examples about the same. We don't have to. We just go to the exercises now. Come on, seriously. K f of x. And that just, you know, makes it stretch vertically. Whatever. Right, whatever. Where are the interfaces? What is this? Phi of x. Is that the Euler-Tocian function? No, that can't be. Algebraic operations on function. If fx and g of x are real valued function of x with domain set A and B, then both fg are defined in A intersection B. Now we define f plus g, f minus g, f times g, f upon g as follows. So f dot g, okay, that's like f of x. Oh, it's not fog. So fog and f dot g are different, I guess. So it's f of x times g of x, this thing, and then of course f of g. So you got an O over here that's actually visible as an O, right? This is the same thing as saying f of g of x, wherever this function is actually defined. Make sense? Okay. Okay, so that's the way you do algebraic operations. I mean, it's just, yeah, why would you ever use this notation? Is there even a use for this thing? I don't know. For domain of phi of x is equal to f of x, so fractional part of f of x to the power of g of x, conventionally the conditions are f of x is bigger than 0 and okay. F of x c n of x, so that's a function, right? Or phi of x is equal to f of x, right? Conditions of domain are f of x is bigger than or equal to g of x, right? And f of x is belonging to the natural number, g of x also belong, and it's belonging to whole numbers. Yeah, okay, but wait, we can define, okay, just move on, no need for negative n values, right? Find the domain of the following. We don't have to do this, we just have to go to the interfaces. Yeah, there we go. First exercise, to the following, okay, we should, oh, you got these many, right? Cool, right, let's do the thing. The first exercise, right? So the following sets is a function. So you got 1 to 4, then 1 to 5. Okay, first one is not a function because 1 to 4 and then 1 to 5. 3 to 3, anywhere. Okay, 2 to 1, 2 to 3, that's not a function. 1 to 2, 2 to 2, 3 to 2, 4 to 2. That's, I guess it's a function because you got 1, 2, 3, 4. All of these are different. And what's about? Oh god, this is just bad. So C is the only function. Next question. If y equal to f of x real to real, which of the following rules is not a function? Okay, so the whole real numbers, right? That set must be completely used. So minus x square, of course, the function. Y equal to x, it's a function. Y equal to square root of x, so it's not defined on all real values. That's a problematic thing, right? So I guess C is not a function. So maybe C. Now it's debatable whether or not it actually take negative infinity, positive infinity into the set of real numbers, but whatever. Domain of the function f of x is equal to 1 upon square root of x plus 2. Right. What about this? Oh, the domain, of course. So x plus 2 must be strictly bigger than 0, not bigger than or equal to 0, because if it's equal to 0, yeah, that's problematic. So what does that mean? X must be bigger than negative 2. Easy as that, isn't it? So negative 2 to infinity, negative 2 not inclusive. This doesn't make any sense. How can you include infinity? So B is the only one. That's the domain. Wait, can you include infinity? I don't know. The next question. I don't think you can ever do that. Okay, the domain of the function natural log. Is this log or doesn't really matter, does it? 3 minus x upon 2. The only thing is like this thing, 3 minus x upon 2, that must be a positive value or equal to 0. But it cannot be equal to 0 because you got a natural log on top of that, or log or whatever. So what does that mean? 3 minus x upon 2 must be bigger than 0, strictly bigger than 0. Which means that x must be strictly less than 3. So negative infinity 3. It's going to be. Next question. Fifth, you got domain of the function cosine inverse of 4x minus 1. So, the domain of cosine inverse is just like negative 1 to 1 inclusive. So what does that mean? 4x minus 1, that must be in this range, negative 1 to 1. So like 4x is in 2 to 0. So x is in 1 upon 2 to 0, right? Makes sense. So 0 to 1 upon 2 inclusive. So B is the answer. Oh, come on. Okay, next. Sixth. Domain of the function log of x squared minus 9 is. By log, you mean natural log? I don't care. I don't care at this point. So yeah, like mod of x squared minus 9, that just must be bigger than or equal to 0. Isn't that correct? Yeah, so the only, wait, it cannot be equal to 0. It's just bigger than 0. Well, that's obvious, right? It's always bigger than 0, except whenever it's equal to 0. So x square cannot be equal to 9. That just means x cannot be equal to plus minus 3, right? Yeah, that's the only condition. So all the real numbers except the set containing negative 3 and 3. So C is the answer. Next question. Seventh is domain of the function f x is equal to square root of x minus 1 plus square root of 6 minus x is. So once again, just want the domain. X minus 1 must be bigger than or equal to 0. So x must be bigger than or equal to 1. At the same time, 6 minus x must be bigger than or equal to 0. So x must be less than or equal to 6. There we go. So 1 to 6 inclusive. So B is the answer. Next question. How many are there? Okay, the domain of the function f of x is equal to square root of 2 minus 2x minus x squared. Factorize this out, of course. Square root of negative, and then you got just want to factor this out first of all. Negative, you got x squared plus 2x minus 2. That's kind of complicated, isn't it? Because yeah, right, you can't factor it out easily. So let me just make a perfect square. So x plus 1 squared minus 3, basically 3 minus x plus 1 squared, right? The square root of that thing. So the condition is that 3 must be or equal to x plus 1 squared, right? Which means x plus 1 must be between square root of 3 and negative square root of 3. Inclusive as well. So x is between square root 3 minus 1 and negative square root 3 negative 1. Makes sense? Which is, I guess, this range. Yeah, B is the answer. Next question. Come on, next question. Ninth is domain of the function sine inverse of 5x. Once again, 5x belongs to negative 1 to 1. X belongs to negative 1 upon 5 to 1.5. What kind of question is this? Ninth B. 10th. Domain of this function. Okay, right. So 1 upon log all that. Right. So first of all, this whole thing cannot be 0, which means 2 minus x cannot be equal to 1. So x cannot be equal to 1. So you cannot have 1 included. Right. What else? Other than that, it can be anything except that it must be defined. So 2 minus x has to be bigger than 0. So x has to be less than 2, right? So what conditions do you have? X less than 2, x cannot be equal to what, 1, yeah, of course, and also x plus 1 must be bigger than 0, right, or equal to 0. So x has to be bigger than or equal to -1, right? So it's like -1 to 1, not inclusive of 1, and then 1 to 2, but it should be not inclusive of 2 as well, which, why is that not here? Why are you, okay, what happens when you put -1 over there? It's like 1 upon log 3, which is well defined, and then square root of 0. What's the big deal? It's still well defined. Uh, yeah, I mean, why not? And the -1 to 2, you are missing 1 over here. What happens when x is equal to 1? Yeah, that's problematic, isn't it? Because 1 upon 0 doesn't make any sense. Why are you including 2? Because when you include 2, you're going to get 1 upon log of 0, and that's not defined. So, okay, none of these are in the options, right? So it's like none. Weird. Next, 11th. If graph of y equal to f of x is as shown in the following is the graph of y equal to f of mod of x, right? So mod of x, right? Just, I mean, first of all, just delete the part of negative x because that doesn't really matter. Only going to deal with positive x values, right? Okay, positive input values for f, right? So for x bigger than 0, of course, or equal to 0, you still got this graph, but then you have to flip this because, right? So for some point over here, okay, just draw this out. So for the, right, so for x bigger than or equal to 0, you got this graph, whatever this might be, and then for, let's just say, some point over here, right? So you got this point, you just take this mirror reflection, right? These two have the same mod of x values, which means they have the same f of mod of x values. So whatever thing happens over here, the same thing should happen over here, and then this thing for all the points. So what does that mean? Just, copy this graph. Yeah. Right, which is option C, I guess. Wait, oh, no, that's actually, this still allowed. Yeah, B is the option. Next, 12th. So the following is a graph of y equal to, so mod y equal to f of x, right? Oh yes, figure out f of x graph. Wait, I think it's the same thing for, oh yeah, so you got this thing, and then just, flip this because f of x works, negative f of x also works, right? Yeah. So, okay, you got f of x as this guy, whatever. So negative f of x, yeah, that's gonna be the mirror image of that about x equal to 0. So, sorry, the y equal to 0, right? The x-axis, yeah. What points are these? -2, 0, 2, 4. Then you got 4, well, whatever. So you got this graph, like, it's so, I know, drawing really bad. Does not even matter. And there you go. This is f of x. This thing is negative f of x. So both of these will satisfy this equation, right? Yeah, I mean, yeah, y equal to plus minus f of x. That's why this thing. So that's the graph, which, what is this? Okay, I guess B is the answer. Come on. Why is it so hard to write nowadays? Just don't have that practice anymore, right? Okay. 13. If the domain of f(x) is 1, 2, then the domain of f of log base 2 of x is, right? So, I mean, of course, this input value, log base 2 of x, that must be, between 2 and 1. Now, the good thing is that log base any positive number, like that's basic, okay, any number bigger than 1, basically. Yeah, that's actually an increasing function because if you take the derivative of this guy, it's just going to be, yeah, 1 upon natural log of 2 times x, right? Yeah, right. Which means that for x being bigger than 0, this is actually, increasing. And then for negative values, it's actually not defined in the first place. So yeah, but if it's increasing, what does that mean? Then you can just apply, or okay, you can do that thing, or instead you can just do 2 power all of these guys, because 2 power x is also an increasing function, and that's in fact yeah, that's actually increasing for all real values. So even if you had a negative one or whatever over here, it's still good, no problem, right? Just two power these quantities. That makes sense. Basically, like 2 is less not equal to x less not equal to 2 power 2 is just 4. There we go. So 2 to 4, that's the domain, right? So 13th b, 14. If the domain f of x is equal to this guy, then the domain of f of cosine inverse of x is what? I think you mean if f of x is equal to this guy, then domain of f of cosine inverse of, right? That's what you should have said, not this thing. But whatever, just figure out the domain of this quantity, right? So you got pi upon, so like pi upon 3 squared basically, minus x squared, that should just be bigger than or equal to 0. So x squared is less than or equal to pi upon 3 squared. What does it mean? X basically belongs to this range, negative pi upon 3 to pi upon 3, right? Okay, and then you are saying instead of x, you're going to put cosine inverse of x. There we go. Cosine inverse of x must belong in this range, right? Yeah, sure. Negative pi upon 3 to pi upon 3. Yeah, I mean, wait a second. That doesn't make any sense, because cosine inverse x cannot be negative. It has to be 0 to pi. Well, oh, of course. Okay, it can only go in this range. Cosine inverse of x actually belongs to 0 to pi upon 3 only. The only thing, I mean, it's okay, that doesn't really matter. It can be anything. Yeah, you get the idea. The only real restriction is that cosine inverse of x must be less than or equal to pi upon 3. That is really the only restriction that you have. Other than that, everything works. No big deal. Yeah, that's the thing. So when will this happen? So pi upon 3 is some place over here. Cosine inverse of x is less than or equal to that, right? So you got all the angles less than or equal to those guys. Those have cosine being something bigger than 1 upon 2. This has 1 upon 2 as the thing, right? So bigger than 1 upon 2. That doesn't make sense, right? So x must be just bigger than or equal to 1 upon 2. Only then can you actually have this thing. Make sense? Right. So yeah, I mean, if you call this angle theta, then cosine of theta is of course bigger than or equal to 1 upon 2, but cosine of theta is by definition x. Makes sense, right? Yeah. So that's the thing. That's what we get. And of course, it's in this function, so like it's necessarily less than or equal to 1. Yeah. So 1 upon 2 to 1, I guess that should do it. Which is not here. What? Negative 1 upon what? No. That just doesn't make sense. Wait a second. What? Oh, it should also be bigger than or equal to 0. That's also important, isn't it? But then, it's already bigger than or equal to 0. What's the big deal about it? That's gonna work out. Oops, it's... Wait a second. I mean, yeah, it's like less than or equal to 1. And 1 is going to be equal to 0. Yeah, sure. And then it goes to 1 upon 2. That should make sense. So really, 1 upon 2 to 1, that should be the range. And why is that not here? So, let's try putting x is equal to 1. What do you get? Like f of cosine inverse of 1, that's going to be f of 0. You put 0, yeah, so like f of 0 is just square root of pi squared upon 9, which is defined. So what's the big deal? Why is 1 not included? It's also none, I guess. Yeah. Okay, it's included in this thing, but then you're also including negative 1. When you put negative 1 in there, the sine inverse of negative 1 is going to be pi. When you put that, yeah, that's problematic, isn't it? Pi upon 3 squared minus pi squared. Guess which one is bigger? Pi squared, of course. So this is going to be negative quantity, which, yeah, that's wrong. So none of these. 14th, none. How do they put questions like these? At the very beginning, they are putting questions like these. I can't believe this. Number of solutions of 2 sine mod of x is equal to natural log of mod of x is okay. So, let's start with something easier. 2 sine x is equal to natural log of x under the restriction that x is, bigger than or equal to 0, right? That's what basically you are saying. So doing this, you'll figure out all the values of x, and once you have all the values of x, you can just, multiply those by number of values by 2. You get the thing, right? I mean, clearly x equal to 0 is not a solution, so all the values you get are non-zero, which means those times 2, number of those times 2. That's what we're looking for. Yeah. So now think about it. Natural log of x, it's like, okay, first of all goes to negative infinity, and then here x equal to 1, it's 0, and then it goes like that. Yeah. And then 2 sine of x, it's like pi upon 2 is bigger than 1, isn't it? Okay, that's when you have the maximum value, right? When is this going to be equal to 1? So that happens when x is equal to e, and e is 2 point something, so it's less than pi basically. At pi it's wait, what is this? I don't know what was that. At pi it's gonna go down to 0, and then some stuff happens, we don't care about that, because the thing is, at pi it's already reached okay, I should rather have like this. It's already at, wait, okay, at pi it's even more than 1, isn't it? So maybe this graph is really deceiving actually. Should be even more steep, so like this, I don't know. Yeah, so 2 point something, that's when, so at e basically it's equal to 1, uh, but e is between pi upon 2 to pi, and pi upon 2 is like 1 is gonna decrease, go to 0. At pi you got something bigger than 1, and then from there it's never going to come down to 1, right? It's never going to come in this range, negative 1 to 1. What does that mean? That means there's only one solution, this solution, right? So two solutions basically, because this solution and a negative of that as well. There we go. So A is the answer. That was a nice question. Next, 16th. Domain of the function square root of, come on, okay. This is defined whenever x is like, that's not equal to 1. Yeah, of course. So x is not equal to 1. That's everywhere. Okay, what about this guy? Sine inverse of this. Okay, that should be defined. So 2x minus 1 upon 3, that should be between 1 and negative 1. Then it's defined. So negative 3 is, yeah, okay, 2 minus 1 is whatever. 4, and that's negative 2. There we go. So it's negative 1 to 2, but it's already less than 1. What does that mean? Negative 1 to 1, huh? Cool. Inclusive. It's less than or equal to 1. That makes sense. So A is the answer. Does negative 1 work? Of course it does for this guy. What about this guy? So, negative 1. That makes sense. So it does work. 1 also works because that's 0, and it's going to be like 2 minus 1 upon 3 shorts. It's going to work. So A is the thing. Next. 17th. 17th, domain of the function y equal to log base 10 of 5x minus x square upon 4 is, come on, seriously. So you got square root, so this must be positive or equal to 0. Okay. What does that mean? Log base 10 of 5x minus x squared upon 4, that must be bigger than or equal to 0, right? So just, do 10 power this stuff. Doesn't matter what value this is, it's real or whatever. Yeah. So 5x minus x squared upon 4 is bigger than or equal to 10 power, which is 1. What does that mean? That means it's automatically, bigger than or equal to 0, because this is like, okay, bigger than 0, strictly bigger than 0. So this is already in the domain of log base 10, right? So that's cool. You got x. Okay, just calm down a bit. Don't rush this. X squared minus 5x plus 4, that goes over here, right? Less than or equal to 0. So basically x minus 4 times, yeah, you can see x just belongs to 1 to 4. Makes sense, right? To solve this inequality. So I guess, yeah, 1 to 4 is the domain. What's tricky about it? That should do it. That should do it. Okay, next. Now you got 18th. 18th is domain of the function y is equal to square root of cosec x plus sine of, oh god. So okay, this thing should be positive. It's like saying 1 upon sine x must be bigger than 0. Clearly sine x must be bigger than 0. It cannot be equal to 0. Makes sense? Yeah. Okay, actually it should be not equal to 0. But you know, it cannot actually go to 0, you know. Yeah, it's already just either bigger than 1 or you get the idea, don't you? Okay, so this is the thing. Sin x is bigger than 0. That's all you are saying from this. And one thought, that's defined for all kinds of numbers, right? Real numbers, that is. So no big deal with that. This is the only thing. That's yeah. So sin x must be bigger than 0. When does that happen? In the first two quadrants. So it's 0 inclusive to, yeah, till pi. Actually pi is also inclusive, isn't it? Exactly. So 0 to pi. But of course this, like both of these guys plus 2n pi, so actually it should be 2n pi to pi plus 2n pi. It's gonna do the thing. Yeah. Oh wait, oh it should actually be bigger than 0, not equal to 0 everywhere. It should just be bigger than 0. Nowhere should it be equal to 0. This is the thing actually, right? So yeah, okay, x is bigger than or equal to 2n pi. That is not equal to, why am I doing this equal to stuff? Less than 2n plus 1 pi. That makes sense? Okay. Or, you know, you can go the other way around. Wait, what? 2 minus 1? No, no, no. Yeah, I guess C is the correct one. And belongs to integers. Cool. So C is the thing. Next question. 19th. 19, you got domain of the function. This, okay, come on, seriously. Yeah, x minus 2 must be bigger than, okay, this must be bigger than 0, strictly bigger than, it can also be equal to, what's the big deal about it? Okay, so x minus 2 upon x plus 2 must be bigger than or equal to 0. You know, draw this out. Negative 2 to over here, it's positive, then it's negative, then it's positive. So the only region is this thing, right? It's like negative infinity to negative 2 inclusive union 2 not inclusive. So because wait, something went wrong. Negative 2 not inclusive because unfortunately at negative 2 this just goes to plus minus infinity, which doesn't make any sense. So union 2 is actually inclusive because that makes it go to 0. Cool, right? That's the thing. Okay, and what else? This thing as well. So you got, unless you get the idea, right? It's going to be negative infinity to negative 1 not inclusive, right? It's pretty much the same thing as that one, just like that. Okay, union 1 to infinity. Just take the intersection of these two guys. That's when this will be defined. Yeah. Which, well, think about it, which of them is yeah, okay, negative 2 to barrel ranges is bigger. So of course this thing is the intersection. Makes sense. Yeah. Oh, it's different. It's 1 minus x upon, okay, this is problematic. It's like x minus 1 upon x plus 1 is actually bigger than, sorry, it's less than or equal to 0, right? That's the thing. So it should actually be, you know, negative 1 to 1, not inclusive negative 1, because it's gonna make it bad. Inclusive 1, that's what it should be, which, yeah, it doesn't fit in the range. So what's the conclusion? No such value of x that, you know, yeah, okay. So D is the answer. 19, 20. Come on, 20. Number of integers in the, no need for the answer key. Number of domain of number of integers in the domain of this. Okay. Of negative 1. So clearly 3 minus x cannot be equal to 1. So, you know, x cannot be equal to 2. Okay. What else? 3 minus x must be bigger than 0, strictly. So x is less than 3. Cool. What else? This thing, standards of, right. So 2 minus mod x upon 4, that should lie between 1 and negative 1. So negative 4, yeah, negative 4 minus 2 is negative 6. Negative mod x is not equal to, that goes over there. 4 minus 2 is just 2 basically. So mod x is bigger than or equal to negative 2, less than or equal to 6. Isn't that right? Yeah, this is obvious. So mod x is less than or equal to 6. That's the thing. So x just belongs to negative 6 to 6, right? But remember, it's actually less than 3. So it should just be negative 6 to 3. But remember that 2 is not allowed. So it's this thing except 2. Yeah, basically. So how many integers in this range? You got negative 6, negative 5, negative 4, and negative 3, negative 2, negative 1, 0, 1, no 2, and once again no 3. So there we go. These are all the integers in there. You got 6 and then 7, 8. 8 integers, which is option B, I guess. Next question, 21. Oh, it's not clear now. Fine. Just check. Okay. So first C, second C, third B, fourth B, fifth B. Makes sense. C, B, B. Ninth B, 10th is supposedly B. We know it's none actually. 11th B, 12th C. Okay. Silly mistake, some kind of, I don't know. Then 14th C. We know it's none. Okay. 15th A, 16th A, 17th B, 18th C, 19th D, and this is B. Okay, cool. So the only one that's weird is 12th. So 12th. Where is the 12th? So B is wrong, and what C? Okay, that is so stupid, right? Of course. Why was this X? Yeah, that is stupid. I just won't allow that. It's just the mirror image, and then C cannot be correct. So yeah, they are wrong. Of course, B is the thing. Makes sense. Okay. Right. Methods of determining range. So this was only domains and stuff. Now you're going to range. Right. We don't need methods. I'm just gonna go to the questions. What is this? Oh, come on. What's happening? Equal or identical functions or whatever. Wait, actually, maybe this might be a definition we need. So two functions are said to be equal if the domains of them are equal, the range are equal, and f(x) is equal to g of x for every x belonging to their common domains. I mean, if 1 and 3 are satisfied, then of course 2 will be satisfied. What's the big deal about it? Codomains, no mentions over here. Okay. What about the codomain? Do we not think about the codomain? Whatever. Okay. Yeah, we don't need your help. We can do it on our own. How many are there? Oh god. 20 of these guys, huh? Whatever. Have to do it. Okay, we should stop for now. Yeah. So I'll complete this later on. So I'll see you in the next video.